Yes, I think uh, we are ready. So,
This call is now being recorded.
good evening, one and all. We have with us our expert for today's session. This is Dr. Mohammad Ahsan Halimi, who is a member of IEEE and has received his MTech degree in Electronics and Communication Engineering from Pondicherry Central University in Pondicherry. He received his PhD degree in Electronics and Communication Engineering from NIT Silchar in 2023. He has worked as a senior faculty at NCPUL Dream Center, jointly run by the National NELIT Chandigarh and National Council for Promotion of Urdu Language and NCPUL New Delhi. He worked in project titled Skill Development in Electronics Hardware during 5th February 2014 to 31st October 2014. He has also worked as an assistant professor at the Department of Electronics and Communication Engineering, Vela Pugdi Ramakrishna Siddhartha Engineering College, Vijayawada, from July 23 to July 24. He is currently employed as a postdoctoral fellow at Interdisciplinary Research Center for Communication Systems and Sensing in King Fahd University of Petroleum and Minerals, Dhahran, Saudi Arabia. He has published 18 journal papers and 9 conference papers. His research interests include RF energy harvesting, RF rectifiers, microstrip antennas, reconfigurable antennas, wireless body area networks, etc. And this is the second session which he will be taking, if I'm not wrong. So I hope you have already attended one of his sessions, and you already know him. So with very short introduction, I welcome Dr. Halimi for sparing his valuable time for the participants here. Sir, thank you, and the session is over to you, sir.
Thank you, sir. Thank you very much for your introduction. Um, I already introduced about myself and my institutes also. And today I will discuss about the background of energy harvesting and some application oriented. So because the topic is about applications in either RF energy harvesting or wireless power transfer for low power electronics. So yesterday we have discussed about how to design rectifier circuits and how to design matching networks. So what is the impacts of matching networks on the performance of rectifier or performance of rectina. And today we will discuss about application of rectina for low power electronics, how rectina can help to power low power electronics. So most of the slide will be common, and we will discuss about applications points of view. So this I already discussed. So we have discussed about okay, let me to introduce in a few sentences. Energy harvesting is actually the process by which energy is derived from external sources and captured and stored for low power devices. And low power devices may be wearable electronics, may be implantable electronics, may be low power sensors like temperature sensors, like humidity sensors, like any types of sensors that can help in our daily lives. So low power sensor can be energized through RF energy harvesting using a retina. So we have two techniques for this. First one is RF energy harvesting, and second one is wireless power transfer. And this is the conceptual block diagram. And this is actually far field WPT. This concept is based on far field WPT, in which the transmitter and receiver, the distance between transmitter and receiver is in such a way so that it belongs to far field. So either we have ambient RF sources or intentional RF sources. Intentional RF sources, we can tune the transmitted power according to our requirement. But for intentional transmit RF sources, we can tune, we can increase or decrease the transmitted power according to our requirements. And but for ambient RF sources, we cannot increase the power because that is that we need to do survey about how much ambient RF power is available surrounding to us. So what is we have abundant electromagnetic energy from various RF energy sources, from Wi-Fi routers and digital television signals, amplitude modulated signal, frequency modulated signal, and GSM and various sources. But this is the application of RF energy harvesting to energize a low power sensor. Here sensor is a watch, LCD watch. Here this is temperature sensor, humidity sensor. So first approach is to, for example, this is the battery unit. For example, this is the sensor, and it required, for example, 1.8 volts. So what will be is the input impedance here? Oh, sorry. What is the input impedance here? Z in. First, we need to calculate, and accordingly, this is sensor. Suppose after calculating this input impedance, accordingly, we need to design a rectifier circuit. The load of the rectifier should be it should be equal to Z in. Z in should be equal to rectifier load. It will be so that here in figure 4 you can see that a 1.8 gigahertz rectina capturing RF energy from this mobile tower, and that after converting into DC through rectifier circuits, it can that DC used to power battery free LCD watch. So in place of battery, this is, suppose this is battery terminal plus and minus, we need to calculate the impedance, and for rectifier circuit design in ADS, we need to we can use this Z in as a load resistance. In place of arbitrary load resistance, we can utilize this Z in. I will show some slides here. And second technique is wireless power transfer. The transmission of energy from one place to another place without using wire can be done through wireless power transfer techniques. Initially, in 1890, Tesla was able to transfer energy from one coil to another coil, and after that, MIT, USA proceed that research and design a Tesla tower, and using these techniques, they able to transfer power from one place to another place for long distance power transfer. But in this process, there was a huge power loss in the air, in the transmitting medium. So wireless power transfer techniques can be used where we have our own intentional transmitter, we can increase or decrease the transmitted power according to our requirements. So WPT, here one of the one application for WPTs. Suppose this is a signal generator amplifier, and using this transmitting antenna, power is transmitted here, using from here to here. Power can be transmitted. Suppose this may be either any biomedical here biomedical devices. So what will happen? Biomedical devices need some power to operate, and where we need that power? From where? It may be through battery, it may be through wireless power transfer techniques, through RF energy harvesting techniques, or it may be battery, but we need to charge the battery after certain time. So we can utilize WPT technique to wireless charging also. So in this scenario, we can utilize wireless power transfer technique. So here we can see this is the transmitter, base station transmitter for power transmission, and this antenna capturing that signal, and we have RF. Then rectifier has been used to convert this RF to DC, and then DC can be used to power the sensor. Now, suppose we have a biomedical sensor, either wearable or implantable. That sensor sensing some physiological data, and that data need to be transmitted to the outside world or the suppose access point. So using this transceiver, this DC here also DC. This DC also can be used to power sensor. This DC also used to power transceiver, and the sensor data. Suppose this sensor sends some physiological data, and that data using this transfer we can transmit, and using this communication link here, if for a if doctor is seated here, so the doctor can see the sensor data, and accordingly they can prescribe some medicine or some suggestions or some medical test based on this physiological data. So using this for this scenario,
Sir,
we can
sir, your slide is not visible.
not visible. 1 minute.
It is not visible from my side.
Okay. Other participants, can you able to see my slide?
It's visible.
Yes, sir.
It is visible for other?
Yes, sir.
Yes, sir, it is visible. Yes, sir,
For me
visible.
also is visual.
Okay.
Yes, visible.
Okay. So using these techniques, first using this WPT here, wireless power transfer, this is data telemetry. So in many research papers, using dual band implantable antenna has been used. One for one band can be used for wireless power receiving, and one band can be used for data telemetry from outside world. And these steps, these things for biomedical applications in general, this dual band antenna for wireless power transfer and data telemetry simultaneously has been proposed in many papers. So these are some examples of wireless power transfer system. So here again, in the previous slide, I already discussed about this scenario. Either using far field or WPT techniques, we can transmit power inside the the retina, implantable retina, and then that retina can be used to power any implantable sensor. Or maybe this scenario can be used for wearable sensor, either wearable or implantable. Here, suppose we have implantable. WPT having wireless power transfer can be done using either far field or near field. In the previous slide, we have discussed about far field WPT, and that used antennas in the communication between two antenna in far field region. So if for near field region, either near field radiative or using mutual inductance between two coils, the near field resonant inductive coupling scheme is the oldest one and most established power transfer method. And using this technique, we can transfer power from one place to another place. And suppose this is inside the body, implantable device. Sorry, if it is inside the body, it is outside. So if suppose we have some implantable sensors inside the body, we can in that case, if we wear the transmitting coils, then there the distance between wearable transmitter and implantable receiving coil will be small, and using this near field resonant inductive coupling, we can transfer power from outside the body to inside the body, and that power can be used to power up implantable sensors. Either this technique can be used for recharging the battery. If we have battery, so we can charge the battery if after a certain time, or we can use this technique to supply the power. In both the scenarios, you can use. Here in figure 11, we have some implantable devices that can be used. The patients, deaf patients, that can unable to hear the sound. So here also I am not going to focus how these sensor working. Just I want to introduce about how WPT can be used to transfer power from suppose this is a transmitting coil, and this is inside the eye wearable. So we can transmit power using WPT techniques. Like here, retinal prosthesis system. So retinal prosthesis device is developed to capture external image using camera. Suppose this is the simplest diagram of this one. Suppose we have some issue to visualization issues. We are unable to see because of the damage of retina. That, but this is not by blind by birth. This technique can be used for those who have age-related some disease after a few age. There will maybe some damage in the retina cell. So in that case, we can use these techniques here. A video camera can capture the image in front of the man, and we have extraocular antennas also. Suppose we have this antenna. Suppose this antenna can, and this is intraocular unit, implantable retinal prosthesis devices, and that devices also need to capture this is the intraocular unit, this is extraocular unit. That there are two types of communication link. One communication link is this antenna to transmit this signals, this image to the inside intraocular unit. And second thing is the antenna can be used for to transfer power to operate this intraocular unit properly. So a retina can be used here also to power intraocular unit for retinal prosthesis devices. Now in figure 13, we have some implantable antennas for leadless pacing system. So if we have leadless pacing system, so this pacing system also needs some power to operate. So using here same techniques we can use to, using wireless power transfer. So again, we can use these WPT techniques for either for retinal prosthesis or any implantable biomedical devices. We can transfer power either using far field wireless power transfer or near field inductive wireless power transfer techniques. So why retina? In previous slide, in previous lecture yesterday, I have we discussed about this Schottky diode modeling. So let me to introduce, and these parameters we can, this PPT we have discussed yesterday. So we have these types of parameters, saturation current, RS, and T0, VJ, and if we design this using any, this is the simple rectifier circuits. And yesterday someone asked about how to check the power conversion efficiency versus frequency, or power conversion efficiency versus load or anything. So that's why I included some slides here. Again, I am showing this harmonic balance. This is HB1, and using parametric sweep we need to check, and this HB1 should be connected here with parametric sweep, and this sweep one can be connected here. So now these three are interconnected. The value of C0, suppose it may be C0, it may be load resistance, it may be input power, any variables, any variable. So this is the the magnitude or variable, and this is RF means resonant frequency, either from 2 gigahertz to 3 gigahertz, or maybe. So using this we can find these types of equation, because here we have C0 naught. So here we can see that by changing the value of CJ naught, 0.2, 0.7, and 1.2 picofarad, what is the impact of? So here we can see if we have different available diodes, which diodes should be suitable for low power, which diodes should be suitable for high power. We can check, we can do this process, this parametric sweep process, and using this parametric sweep process, we can check, find these types of graph, and here we can see that CJ naught. Okay, 1 minute. This is related to 0.2 picofarad, here 1.2 picofarad. Here we can see that if CJ naught should be low value. From data sheet, if we have two diodes, one diode having CJ naught X, second diode having CJ naught 2X. So we need to go through this using these types of performance parameters. Again, if we change here, in place of CJ naught, if we put here RS, so in that case we can find the impact of RS either for 5 ohm, 15 ohm, and 25 ohm value, and if RF is less, the performance efficiency will be better. Similarly, suppose this is input power dBm. So x-axis, this is x-axis Pin. Now, here sweep wire is input Pin dBm. If we change this into RF, here RF gigahertz, this RF gigahertz. If we change this into RF, so we can find the efficiency versus frequency. If we change this load, this is R. If we suppose here variable, this variable, if we put here, if we put here load, add one variable, load is equal to any 8 kilo ohm or anything, or 820 ohm, any value. So in that case, if we put here in place of P input, if we put load, then we can derive efficiency versus load. And in that conditions, as we discussed in the previous slide, we have a 3 variable. One is input power, second variable is frequency, third variable is load. For this, if we put here RF, then here we should if we put here RF, then here we put P in, here we can put RL, load, and accordingly we can check the performance with respect to load, with respect to frequency, with respect to any variables we can find using harmonic balance and parametric sweep. And this was the one of the question yesterday someone asked, so I include. And here also some saturation current, impact of saturation current, because we have parameter IS also, saturation current 0.05 microampere for HSMS 2860. So here we can see whether IS should be high or low for better performance, better efficiency. Here we can see the impact of VJ on the efficiency. It has not that much impacts. So here using this graph, we can see that CJ having more impact on power conversion efficiency. This also having more impact on power conversion efficiency. This having very less impact on power conversion efficiency. So using this graph, we can decide we should focus on which parameters from the data sheets, spice model of the data sheets. Here, this is a breakdown voltage. We can see breakdown voltage having similar performance up to certain level. But after that, if breakdown voltage is less, 5 volt, diode can operate up to 10 dBm. If it is suppose 15 volt, it can operate up to this much level. If breakdown voltage is more high, it can operate up to more power. And if we have apply power more than this, the diode will burn and rectifier will not operate properly. So using these performance parameter, we can find we can utilize this performance parameter for selection of proper diode, selection of which diode should be better for which condition, which power condition. For low power rectifier, which diodes will be better, which with different parameters. So already we have discussed about this. And why retinas? Already multiple times we have discussed, and the different components: receiving, harvesting antenna, filter, matching networks, and this is the retina design procedure. So first, we have to define the goal for what purpose we are going to design a retina. So first, we need to design antenna. Define the goal of antennas, either for single band, multi-band, or broadband antennas, or antenna array. Sometimes antenna array we can use to capture more power, because antenna array can have more gain. So using if we see the phase transmission equation, we can see the impact of a gain of a receiving antenna. So we can first we need to define about the goal and performance parameter, like bandwidth of the antennas and the gain of the antenna. If we have a size of the antennas, for implantable we have size constraint, and for variable or for other we don't have that much size constraint. So size is also responsible. Constraint is very impactful for implantable retina. So these types of performance parameter first we need to fix. Operating frequency, bandwidth, gain, size, polarization, because polarization, circularly polarized antenna can capture power even after some misalignment between transmitter and receiver antennas. Orientation, so circular polarization maybe. So first we need to define the performance parameters, our goal in terms of performance parameters, and we need to check these performance parameters. So after checking, if goal achieved, we can go for fabrication and measurements. Otherwise, we need to optimize antenna circuit parameters, and we need to follow this loop until we get the desired performance. So after designing antenna, we can design this antenna using either CST HFSS. We need to design a rectifier circuit. So second procedure is about rectifier. So for designing a rectifier, first we need to define the goal about rectifier, like bandwidth, resonant frequency, efficiency, FR, efficiency, V out, like that. So selection and modeling of diodes. In the previous slides of other PPTs, I have shown the how we can select the diodes. Some using some performance parameter, using parametric sweep. We can see that is fixed. That slide is also enough to check the proper, select the proper diodes. But for learning purpose, you can also do the same process. And then topology, either voltage double series or shunt. Then impedance check. We need to check the impedance, input impedance of rectifier. One thing, we have antenna, we have rectifier, Schottky diodes, RL, see DC pass filter, and this is Schottky diode, and this is antennas. So how to design a matching net? This after, if antenna capture the power, it need to be transferred to rectifier circuit. So we have two things. First one is we need a matching networks, and second one is we don't need a matching networks. If we design impedance Zin, and if we design this first and antenna second, then what will happen? First calculate Zin, then antenna ports input, if Zin is equal to x minus jy, sorry, x minus jy, put the feed x plus jy. If we design rectifier first, just select the this, just calculate the input impedance and put the complex conjugate of this input impedance to the rectifier antenna port. In general, in HFSS or CST, we are putting the port impedance as a 50 ohm. In place of 50 ohm, we can fix that. We can change this 50 plus J0 into a complex conjugate of the rectifier. So in that case, we need not to design a matching networks. So this, otherwise, if we go this as a first, this as a second, then this will be for 50 ohm, based on the 50 ohm. Then we need to use a matching networks, and we need to transform this x plus jy into 50 ohm. So we need to check the performance of rectifier, efficiency, V out, S11, resonant frequency, and we need to optimize matching circuits. And after getting a good performance, we can convert it into rectina. Rectina is rectifier. So rectifier we can design using ADS software. Using ADS software, and antenna we can design using HFSS or CST, or there are many other tools also, Sim for Life or FECO. But for rectifier circuit, ADS is good. So using ADS we can design rectifier, using HFSS or CST we can design antennas, or after that we can convert it into rectinas. This is, for example, this is a rectifier. This is antenna. This is rectifier. Then we can convert it into rectina using this coupler. We can add these antennas and rectifier to convert it into rectina. So these are all about rectina circuits, and these are conclusion. Rectina can be used for not only for a wireless sensor. It may be used for wearable biomedical sensor or implantable biomedical sensor. And if you want to design antennas, suppose antennas for biomedical application, so in that case, use this software, dielectric properties of body tissue. Using this link, you can use this link, and suppose at what frequency, body having different frequencies. Suppose we have 100 megahertz, or suppose 900 megahertz. We are designing to implantable antenna at 900 megahertz. So 900 kilo mega, 900 megahertz. Go all tissue single frequency. Go to this. This is at 900 megahertz. We have conductivity 0, air conductivity 0, relative permittivity 1. This is either for any frequency it will be same, except wavelength. So if we want to design a bone, okay. Okay. Suppose we have a bone. Above bone we have muscles, then fat, then skin. These are for phantom design, and we can go this fat. Where is fat? Here you can find the all the parameters for fat, and this is the conductivity, loss tangent, of fat, muscles, and bones. Also you can find here bone, skin, dry skin. So you can take now for 2.4 gigahertz in place of 9. If we 900, 2.4 gigahertz, it may have some different properties. We can find here, or we can go for here skin. So suppose we need to find tissue is, suppose, blood. What is the impact of blood? Frequency is any frequency, arbitrary. Go at particular frequency. We have conductivity of blood, relative permittivity of blood, loss tangent of blood. Similarly, we can find using this liver, heart, muscles, or any. Sorry, suppose skin dry. Go this. We can find using this technique. We can design a phantom, and what should be the thickness of muscles, thickness of fat. It depends on person to person, and you can follow any base paper of any good journal. And if you want, we want to find the specific dielectric properties, we can go through this link, and we can design the antennas for implantable purpose. So I have not that much expertise on implantable antenna design. So this is all about this. Uh, thank you. Thank you very much for listening. Hello. Hello.
Hello. Hello.
Yes. Yes.
Sir, I wish to design implantable antenna means if for endoscopy applications,
Yes.
wireless power transmission for endoscopy applications. Do we need to design a rectangle kind of, or means the total battery along with the sensor, the total we have to design as a capsule?
Yeah. First things is in the
How do
most
I
of the
need to
paper,
proceed?
people are designing antennas and taking the performance um, of antenna only. If you want, we want to focus on complete system level.
Okay.
For system level, we need to do all these things inside the capsule. And for designing antennas, the surrounding blood or phantom mass, also different body tissue should the dielectric properties we can calculate using that link, and you can. But in most of the paper, in IEEE paper journals, people are working on antenna level mostly, and in few papers or in nature journals, we can find the system level work also.
Okay. For wireless endoscopy, we need to start with the rectana first.
I have not that much expertise on endoscopy and implantable, so you
Okay.
need to
Okay.
go uh, through the any
Journals. Okay.
transaction paper. Focus on transaction papers. Their data will be appropriate, and either for nature communication journal also having these types of publications with system level also. So you can
Okay.
follow that.
Okay. Sir, very nice presentation, sir. Thank you so much, sir.
Thank you.
Thank you for the information, sir.
Hello, very good evening, sir. Sir, I have one query that regarding the body tissues and antenna which we have to make, which software is better, HFSS to use or CST? Because both offers, but which one is more compatible?
Actually, this question I also asked many persons, so and everyone suggest about CST, because in HFSS we can model the body tissue about rectangular, homogeneous or heterogeneous. Okay, but in CST we have mm, the phantom of the heart, phantom of the hand, or different parts of the body. So CST will be better.
Okay, thank
But
you, sir.
in HFSS we cannot change the body properties, and for implantable case, CST is better.
Thank you, sir.
Sir, very good evening, sir. I am Bhavani Shankar, sir, from Annamalai University. I have a doubt, sir, in CST software.
Yes.
Hello,
Yes.
sir. In the day before, you said the CST software is user friendly for students, sir. Now I download it and work for some time, sir. But I face a lot of difficulties in CST software. Any authorized any authorized program examples is available in CST software right now, sir?
I am also not working on my most of the work is on